Good afternoon. You are on the Optimistery channel. Subscribe to the channel. A lot of interesting and mysterious things are ahead. Today we are going to uncover the mystery of volcanoes, which hold great power and which are not fully explored. Scientists have discovered the true power of a huge volcano erupting off the coast of Tonga. Volcanoes often fit a certain stereotype: constant steam and dramatic eruptions. But some of the most formidable volcanoes differ significantly from this image. They remain quiet and deadly, often going unnoticed, especially underwater. Alarmingly, the largest underwater volcanoes have a 360% increased risk of sudden eruption, which is called the Volcanic Explosive Eruption Index of the phenomenon. This phenomenon is comparable in magnitude to the 19th century eruption of the Katoa volcano and has the potential to destroy our world. We explore the intricate details of how this volcano could change life as we know it. Volcanoes, often seen as relics of the past due to rare eruptions, continued to harbor the catastrophic potential of the volcano Hunga Tonga Hunga High Volcano, located in the South Pacific Ocean, is of great importance, located along the Kermadec Tonga Range. The convergence of the Pacific Plate and the Indo-Australian Plate has created a chain of islands and volcanoes, mostly submerged underwater, with only two small islands of Hunga and Hunga Pai visible, indicating volcanic activity underwater. The landscape of the volcano has been shaped by previous eruptions, changing its appearance with each new event, with evidence of eruptions dating back to 1108 AD. Recent eruptions in 2021 and 2022 have increased the risk of sudden eruptions beyond previous expectations. On December 20, 2021, a significant eruption occurred with the formation of a large ash plume visible from New Alofa. The abrupt nature of the eruption led to the immediate issuance of advisories to airlines. Explosive sounds were heard up to 110 miles from the epicenter of the eruption. This initial eruption continued into the early morning hours of December 21st. Satellite images from December 25th showed the island expanding, which was somewhat expected based on previous models on January 11th. The volcano reawakened on January 14th with eruptions of increasing intensity, with the volcanic plume reaching 36 miles into the mesosphere, generating shock waves felt as far away as the United Kingdom and loud booms reported in Tonga, Fiji, New Zealand, Australia, and Alaska, 6,200 miles away. The eruption surpassed even nuclear explosions in its power, as evidenced by a study published in the journal Science Advances. Sam Purkis, a marine geophysicist at the University of Miami and lead author of the study, compared the force of the eruption to that of a hydrogen bomb. The scale of the eruption was unprecedented in recent history, as evidenced by a comprehensive analysis of satellite data, field observations, and drone mapping. The research team's interdisciplinary strategy allowed them to model the eruption and its subsequent consequences, including colossal tsunami waves. The study examined the mechanisms of tsunami generation, hinting at the possibility of a more significant disaster in the future. An unprecedented amount of water vapor, equivalent to 58,000 swimming pools, was released into the atmosphere. This influx of water vapor has implications for the global climate, potentially contributing to temporary warming. Given current climate change concerns, the additional heating could exacerbate the situation. Even more surprisingly, the eruption broke the unprecedented record for the highest volcanic plume in satellite history, spewing ash a staggering 36 miles into the atmosphere. In addition, the eruption produced atmospheric waves traveling at an astounding 720 miles per hour and circling the globe several times after the eruption. Researchers, including Shane Cronin of Oakland University, conducted detailed damage assessments on the ground, landscape, including the Oakland area. The landscape demonstrated the destructive power of the eruption, fallen trees and vegetation along the coast. This physical evidence complemented the survey results, confirming the magnitude of the event that echoed throughout the region. The peak of the eruption manifested as a sequence of eruptions ranging from relatively minor to cataclysmic. Observers reported 2 initial explosions, probably of limited impact, followed by 2 subsequent, much louder explosions that initiated the first destructive tsunami waves. The climactic 5th explosion was the most powerful in its force, comparable to the most significant U.S. nuclear tests. This explosion caused an extraordinary displacement of seawater, triggering a massive localized tsunami at the epicenter of the blast, and people would have been stranded on the open seabed immediately after the eruption, a scenario unthinkable minutes before. According to ground-based observations, the wave height was as high as 45 meters, although experts believe that this value may be underestimated. Such cases are rare, so it is important to conduct extensive research. This behavior resembles that of huge ocean waves at sea, which lose their destructive impact once they reach land. The waves from the eruption slowed as they hit coral reef platforms, but continued to move through shallow water. A notable observation was the convergence of waves from various explosions, increasing the threat of tsunamis. The waves were not just coming from one direction, but seemed to attack from everywhere. The most powerful explosion occurred when seawater hit the hot magma, causing an eruption with the release of steam. The first 4 explosions split the rocks, allowing much of the rock to collapse, letting a significant amount of water into the magma chamber. Research has not focused on the details of the beginning of the eruption. Some researchers have proposed the magma hammer theory, suggesting that the rhythmic movement of magma within the volcano triggered the eruption. Seismic records showed a unique pressure drop during the largest explosion uncharacteristic of volcanic eruptions. This eruption, which began in December, was distinct and occurred more than originally thought. The exact initial triggers remain unknown. Sam Purkis emphasized the unpredictability of volcanoes, which awaken periodically, and magma moves along complex pathways where anything can happen. Study co-author Dan Slayback discussed the unexpectedness of such a large-scale event, despite previous smaller-scale eruptions that have provided some insight. But the power of the volcano still surprises. The magnitude of the climax stunned many, with Slayback calling it a once-in-500-years event, potentially global. The study recognizes the possibility of a large number of casualties, reminiscent of the catastrophic eruption of Katu volcano. The quick response of locals and the reduction in tourists, partly due to the ongoing pandemic, helped prevent the worst effects, which is not usually the case when major volcanoes erupt around the world. In addition, the eruption, which occurred during daylight hours, helped minimize casualties. Detailed analysis of the eruptions provided valuable insights into volcanic tsunamis. This information can help improve early warning systems and community preparedness, impacting regions far beyond the immediate impact zone. Purkis emphasized the importance of the event, stating that while it had serious consequences, it will not be remembered in the same way as the 1883 Katu eruption, also known as Katu. It remains one of the most destructive volcanic events in recorded history. It had far-reaching, catastrophic effects on the local region and significantly affected global climate and atmospheric conditions. Katu was classified as a stratovolcano with a characteristic composite structure. Stratovolcanoes accumulate over time through repeated eruptions of lava ash and a variety of volcanic materials. These materials form layers that form the characteristic steep slopes and visually prominent profile of stratovolcanoes. Prior to the catastrophic eruption of 1883, Katoa was showing signs of awakening after centuries of relative dormancy. A series of small eruptions and increased seismic activity were observed in the vicinity, indicating increased volcanic activity. Volcanic processes are often associated with the movement of molten rock in the Earth's crust. When magma rises to the surface, it can fracture surrounding rock, generating detectable seismic waves using a seismograph. Seismic waves generated by seismographs provide vital insight into the movement and behavior of magma within a volcano. In the case of Katoa, increasing seismicity indicated that magma was advancing toward the surface, and this magma advancement may be causing pressure inside the volcano. The seismic activity served as a harbinger of the strong eruptions to come. The sequence of small eruptions and events in 1883 signaled a gradual escalation of volcanic activity. This escalation is characteristic of the life cycle of a volcano. As magma continues to rise and accumulate near the surface, pressure within the volcano can build up, and this escalation can translate into increasingly violent eruptions when the pressure is eventually released during this period. Regional scientists and observers would record an increase in volcanic activity, and eruptions would likely be marked by the release of ash vapor and small lava flows, signaling the approach of a significant event. The accumulation of pressure and magma in the Katoa system reached a critical point in August 1883, resulting in an eruption that was one of the most powerful and destructive eruptions in recorded history, lasting from May 20th to October 21st, 1883. It was classified as an AN-type eruption and was characterized by high explosive force, forming a colossal volcanic column and emitting huge amounts of ash and gases. The eruption was given a volcanic explosivity index. The volcanic explosiveness index was 6 points, which is the same intensity as the eruption of Hunga Tonga volcano and leads to their comparison. Approximately 20 million tons of sulfur dioxide was released, forming sulfuric acid aerosols in the stratosphere and affecting the global climate. This release caused a temporary drop in global temperature of about 2 degrees Celsius. The immediate effects of the eruption resulted in deaths from thermal damage and tsunamis, with death tolls ranging from 41,000 to 120,000. The far-reaching effects of the eruption sparked renewed interest in volcanology, which recognized the extensive consequences of volcanic eruptions after 1883. The only standing volcanic island in the Sunda Strait was destroyed, leaving behind a flooded caldera. Subsequent volcanic activity altered the underwater topography, and anak cattle appeared in the caldera, symbolizing the volcanic rejuvenation of the region. In contrast to the temporary geographic changes, anak remained active, indicative of ongoing tectonic forces and crustal movement. Although no eruption compares in magnitude to Krakatau, local communities continue to thrive near the active volcano. The question arises whether the powerful eruption of Hunga Tonga is an isolated event. Despite the unexpected eruptions of 2021 and 2022, the volcano has not been inactive, manifesting significantly in 2014-2015, and submarine eruption became significant during this period. The geologic event shaping the Pacific landscape occurred underwater, and surface manifestations of the eruption only hinted at the underwater activity that led to the formation of a new island near Hunga Tonga. Shield volcanoes, commonly referred to as the gentle giants of the volcanic kingdom, have a unique appearance and geologic behavior that distinguishes them from other varieties of volcanoes. These imposing structures are characterized by broad, low profiles that extend over wide areas. In contrast to the explosive nature observed in some other types of volcanoes, shield volcanoes eject predominantly liquid lava, which promotes smooth flow, allowing it to travel long distances, slowly forming the characteristic broad base of the volcano. The relatively liquid composition of the lava plays an important role in forming the gentle slopes that define shield volcanoes. Hawaii is home to some of the most emblematic shield volcanoes, including the famous Moloa and Kila for thousands of years. These volcanoes have actively shaped the topography of Hawaii, increasing land mass through constant eruptions. But the 2018 eruption of Kila was unrivaled. Unexpectedly beginning on May 3, 2018 and culminating on August 6, 2018, it caused havoc in the lower Pune area, destroying numerous residences, flooding residential neighborhoods, and irrevocably altering countless lives. It was dubbed the Fisher Eruption. The eruption altered the southeastern landscape near the park and caused seismic activity, ash emissions, and caldera collapse. The scientific community was stunned by the sudden and escalating development. NASA, along with partner satellites, was instrumental in gathering crucial data on the eruption's trends and atmospheric effects. The phenomenon also facilitated the development of instruments that measure lava flow, velocity, and volume, essential for understanding volcanic models that had not previously been tested at this scale. Conversely, cone volcanoes, smaller but formidable volcanic relatives, exhibit unique conical structures resulting from gas and ash eruptions. These volcanoes may be smaller than their shield or strata counterparts, but have significant explosive potential and can eject ash and debris into the atmosphere, creating a stunning spectacle. As an example, the Paricutin volcano in Mexico emerged from a cornfield and flooded the town of San Juan Parangaricutiro with lava in 9 years, demonstrating the unpredictability and potential destructiveness of such volcanoes. In addition, there are stratovolcanoes, which are characterized by impressive heights. Stratovolcanoes are characterized by their imposing height and steep slopes consisting of alternating layers of lava ash and volcanic debris, each reflecting a different eruptive phase, indicating the historical activity and development of the volcano. Stratumvolcanoes are notable for their structure and hazardous nature. Capable of eruptive volcanoes are notable for their structure and hazardous nature, capable of explosive eruptions affecting both their immediate surroundings and the wider atmosphere, emphasizing the large-scale impact of their eruptions. Well-known examples are the St. Helens volcano in the United States and Mount Fuji in Japan, which attracted worldwide attention with its eruption in 1980, which unfortunately killed 57 people and caused significant damage. Mount Fuji, which is the highest peak in Japan and the quintessential Stratus volcano, remains an impressive geological wonder, but often overlooked is the fact that Mount Fuji, whose last eruption was recorded in 1707, is still classified as an active volcano. The eruption of Mount Fuji in 1707 has gone down in Japanese history as a pivotal event. The event occurred between December 16, 1707 and January 1, 1708, and covered nearby cities and towns with a thick layer of ash and debris, with the resulting fallout negatively affecting agriculture. Ash threatened crops and farmland. This interference with agricultural activities likely caused food shortages and financial disruption in the affected communities, becoming an unforgettable source of devastation. One of the most important and earth-altering episodes was the volcanic winter of 536, which plunged the globe into prolonged darkness and extreme cold. This catastrophic event is considered one of the most intense and prolonged periods of climate change. The specific origin of the eruption remains unclear. Given the vastness of the regions affected, it could have occurred anywhere from Iceland, North America, Indonesia to South America. But its effects were felt far beyond Europe, with effects reaching as far as China and the Middle East, where unusual climatic conditions were recorded. The eruption released significant amounts of sulfate aerosols into the atmosphere, which prevented the passage of sunlight and caused a climatic cooling that lasted for several years. By March 536, observations of dark skies and falling temperatures signaled the beginning of extensive changes in global climate and ecosystems. This abrupt climatic shift was exacerbated by subsequent volcanic activity, resulting in an additional temperature drop of 2. A volcanic eruption in 547 caused a further 2.5 degrees Celsius drop in temperature, leading to an additional 2.7 degrees Celsius drop in temperature between 539 and 540. Another volcanic eruption in 547 prolonged the cold climate and led to the resumption of the Ice Age. A repeat of such an event may seem unlikely at present, but the eruptions at Hangtang were relatively powerful. The current problem is the increased susceptibility of Hangtang to future powerful eruptions. If such an event were to occur, it could return the Earth to eras of disaster, a resurgence of famine, and disease may be inevitable, and this time, survival may be more difficult. Thank you for watching. All the best to you.